Our project is the Eriez 75B high deflection vibratory feeder tray. The Model 75B is designed for use with medium duty materials such as cereal, dirt, rocks, and other things. The picture below is of a model we made of the tray. Here's a short clip of the tray in use. As you can see, it evenly feeds the material down the tray using a vibratory stroke from the drive motor. To explain tray stroke a little better, we have this diagram. As you can see in yellow, the tray stroke is the vibratory motion of parallel to the drive motor. In this instance, Eriez increased it from 70 thousandths to 90 thousandths. That is not to scale, but the 90 thousandths would be pretty hard to show in a picture. In purple, you can see the parabolic path of material as it flows down the tray at a certain feed rate. Eriez came to us with a problem of losing business to rival feeder tray companies who've achieved a faster feed rate. Eriez currently uses a 70 thousand stroke, and their competitors have achieved an 80 thousandths. Eriez wants to increase theirs to 90 thousandths. An increased stroke results in a faster feed rate. The tray experiences higher internal deformation and stresses at this 90 thousand stroke. Some requirements they gave us at the beginning of this project was to make sure the design does not yield from fatigue due to increased vibratory stroke, primarily weld fatigue. We needed to keep the existing dimensions of the tray envelope, use materials familiar with Eriez, and able to be manufactured in-house, and it easily attaches to the existing vibratory drive motor. Our project goal was to reduce the internal stresses and deformation due to the vibration throughout the tray while keeping the weight and cost increase minimal. We achieved this with a unique brace design attached to the bottom of the vertical drive arms, as you can see highlighted in orange. Here's a clip from the FEA analysis of the internal deformation without the brace. This was the current state of the tray at 90 thousand stroke. Here's a clip of the internal stress without the brace at the 90 thousand stroke. The brace design was made in order to keep unwanted deflection in the y-axis of the drive arms, in turn reducing the stress. Here's a clip of the internal deformation with the brace. As you can see, it's dramatically reduced by 67%. Here's the internal stress with the brace, also reduced by around 60%. A very important part of this project was brace tolerancing and making sure that it will fit every time it is manufactured. These are the tolerances we used as a drawing in order to make that possible. Another issue would be the bolt hole alignment, since it will be bolted to the bottom of the drive arms. We used this drawing here in tolerancing to make sure that it would fit every time. It will be bolted with floating fasteners, as you can see by that diagram to the right. One of the analyses we did was the local and global impact. The electromagnetic drive produces no emissions, which makes it very eco-friendly. The higher tray stroke moves material faster through an automation process. More profit leads to higher pay, better benefits, and more jobs. Manufacturing is also a massive driver force behind technology-driven productivity growth. More competition is more innovation. Thank you very much, and we wanted to make a special thank you out to Jason Benser, which was our contact at Eriez, who helped us out a lot along the way. as well as Shannon Sweeney, who is our project advisor.